Good morning. So, in the last class we have started our discussion on multi-layer neural network or multi-layer perceptron, which is used for pattern recognition purpose. And we were talking about how to adjust the weight vectors or how to train the neural network, so that it is ready for recognizing the unknown feature vectors. So, what we were talking about is something like this. So, we have a multi-layer neural network with a number of input nodes, and the network has a number of output nodes, where the number of input nodes is same as the dimensionality of the feature vector. So, it is dimension of feature vectors. And at the output we have, say, the number of nodes, which is same as number of classes. And we have one or more hidden layers, where hidden layers will also have a number of nodes. And typically, as we said, that the number of hidden layers, if we have say around 2 hidden layers, so that total we have 4 number of layers, including the input layer and the output layer, that is mostly sufficient for most of the practical applications. And what we do is, you feed the feature vector to the input layer and get the output from the output layers. And every node of the input layer is connected to, is feeding the input to every node in the layer above it. So, it goes like this. Similarly, here so, if I consider a kth layer node, the output of the ith node in the kth layer is represented by x I k. So, this is the output of ith node in kth layer. Okay. And the connection weights from an ith node in the k minus first layer to a jth node in the kth layer is represented by w I j k. Okay. So, given this, and as we said that for training the neural network, as we are inputting all the training feature vectors, and we know that what is the class belongingness of the training feature vector. So, from that knowledge, I know that if I feed a known vector or a training vector as input to the neural network, I know what will be the corresponding output, because for every training vector its class belongingness is known. Okay. So, if I get any vector from the output which is not same as the expected output, then the difference between these two vectors is the error vector, and from that we compute the squared error. And training of the neural network aims to adjust the weight vectors in such a way that the sum of squared error, that is minimized. Okay. So, what we have assumed is, say we have capital K number of layers, so that the output layer is labeled as capital Kth layer. Okay. So, given that the sum of squared error is defined to be half then x j k, where this k is capital K, indicating that this is the output layer node, minus d j, that is the target output, expected output of the jth node in the kth layer, take the square of this, where this j will vary from say 1 to m k, where m k is the number of nodes in the kth layer. Okay. And we have seen that for designing or for deciding adjusting the weight vectors, we follow the gradient descent approach, and we have to take the derivative of this with respect to w I j k. Okay. And using that derivative, we have to go for adjusting the weight vector following the gradient descent approach. So, what we have done is we have taken the gradient of this del E upon del w I j k, and we have seen that this derivative comes out to be x j k minus d j into x j k into 1 minus x j k into x I from layer k minus 1. Okay. So, this is what we have seen in the last class, and following this, the weight updation rule will be of this form w I j k in iteration say t plus 1 from the weight vector in iteration t. Okay. This will be simply w I j k t minus eta times x j k minus d j into x j k into 1 minus x j k times x I k minus 1. Okay. This is the weight updation rule. Now, over here, for simplicity of expression, this particular term x j k minus d j into x j k into 1 minus x j k, this we can represent as delta j k. Okay. So, our weight updation rule will be w I j k in iteration t plus 1 will be w I j k in iteration t minus eta times delta j k into x I k minus 1. Okay. So, you find that for adjusting the weights, what we do is you start the error at the output layer, you start with the error at the output layer, take the gradient of it with respect to w I j k, then you adjust all the weights, connection weights from the k minus first layer to the kth layer. Okay. Then whatever error you get in that layer, using that you adjust the weight vectors from k minus second layer to k minus first layer. Then you come to k minus third layer to k minus second layer, and so on. So, you find that we have an information flow in two directions. One is from input side to the output side when we go for computation of the outputs of different nodes, and secondly, for weight updation, what you do is you basically propagate the error term from the output layer to the input layer. Okay. So, that is why this sort of network is called feed forward and back propagation network, and the corresponding neural network learning is called back propagation learning. Okay. So, your vector information or the input vector information or output computation proceeds from the input layer to the output layer, whereas while training the weight updation that proceeds from the output layer to the input layer, that is in the backward direction. Okay. So, this is called feed forward, but back propagation network. Okay. So, accordingly the learning, that is also called back propagation learning. Okay. So, let us see that what will be the steps of this back propagation learning. Obviously, in the first step I have to initialize Wij okay, for every weight vector, for every connection weight, for every node I, for every node j, and for every layer k. Okay. And this initialization has to be made randomly. Okay. So, you set or initialize the weight vectors Wij randomly. Okay. So, after you initialize the weight vectors, the next step will be that I have to feed training vectors or training samples to the input layer. Okay. So, once I feed the training samples, then using these training samples and whatever the random weights that has been initialized, using that I have to compute the outputs from all the nodes from all different layers. Okay. So, the next step will be the feed forward pass and in feed forward pass I have to compute the outputs of every neuron in every layer. So, for k is equal to 0 to capital K minus 1, I have to compute x j k plus 1, okay, which is nothing but that nonlinear function of sum of W I j k plus 1 times x I k, where the summation will be from I equal to 0 to m k, okay, where m k plus 1 is the number of nodes in the kth layer, because one of the node will be used to take care of the bias weight. Okay. So, this I have to compute for every node j is equal to 1 to m k plus 1. Okay. One of the other nodes will have a constant input. Okay. So, this is what I have to do for in the feed forward pass, where I am computing the outputs from every node in every layer depending upon the weights that I have till that time and what is the input vector that is fed in. Okay. So, once all these outputs are computed, now you come to the output layer node. At the output layer node, I know what is the target output and what is the output that is computed from here. Okay. So, from these two I will get the error, and using this error now you follow the back propagation part, back propagation procedure to keep on adjusting the weights, so that error is minimized. Okay. So, the fourth step will be the back propagation part, okay. So, in back propagation what we do is, First, we have to consider the output layer nodes. So, for nodes in the output layer, that is j is equal to 1 to m k, where k, this k is capital. Okay. I have to compute delta j k, which is equal to x j k into 1 minus x j k into x j k minus d j, which is exactly same as this term. Okay. X j k into 1 minus x j k into x j k minus d j. Okay. So, this is what you do for the nodes in the output layer, but you find that computation of this term, this increment term, for the input layer nodes or for the hidden layer nodes has to be slightly different, because there the contribution to error is because of propagation from various other nodes. Okay. So, for other nodes, for layers k minus 1 up to layer 1, this computation will be slightly different. So, here we say delta I k, that will be is equal to x I k into 1 minus x I k. Then I have to have this summation term, because I have the contribution of various nodes leading to this particular error. So, this will be delta j k plus 1 into w I j k plus 1, where this j will vary from 1 to m k plus 1, and this I have to compute for I is equal to 1 up to m k, where this k is lowercase. Okay.
Sir, even for the output layer,
at the output layer I can directly compute the error, because I know what is the target output. But in case of hidden layers, I do not know what is the target output from the hidden layers, because that is coming due to contribution from various other nodes. Okay. So, this direct computation that I have done at the output layer, that is not possible in the hidden layers. Okay. I am not showing this derivation of this, but following the summation from various outputs, okay, and taking the derivative of this, you can find out that this delta I k will come out to be of form something like this. Okay. Because at the output layer I know what is the target output, but in the hidden layers I do not know what is the target output. Okay. Because it is getting combined from various nodes from the layer below that. So, once I have these delta terms, then comes the weight updation part. So, I have to update the weights. And that weight updation is simply w I j k, I will put it as t plus 1 will be equal to w I j k t minus eta times delta j k into x I k minus 1. Okay. So, why I have put this delta term is that having different computations of this delta value, I can have a single expression for weight updation rule. Okay. And all these steps are to be repeated. So, sixth will be repeat steps 2 to 5 until convergence. Okay. So, what is our condition for convergence? The condition of convergence can be either all the training samples are correctly classified without updation of the weight vectors, without updation of the connection weights in a single pass, okay. Or the output error that I get, the output error is limited, it is up to a tolerance level. Okay. So, if one of these two conditions are satisfied, then we can say that the algorithm has converged, and whatever the connection weights we have at that point of time, the network has to work with those connection weights. Okay. So, that is what is the backpropagation neural network, and you find that the backpropagation neural network works with the continuous inputs. That means, the input vectors can be of any form, it can be either discrete input vector or it can be continuous output vector. Okay. There is another kind of neural network which is also used for pattern recognition purpose, and that neural network can be used for recognizing the binary patterns. Okay. So, this is what is called Hopfield network. Or this also works as, the way it works is something like an associative memory. Now, what is this associative memory? You find that suppose you have met one of your friends, one of your school level friend at this age, okay. Possibly after your fourth standard or fifth standard, you have not met him at all, right. And you find that during this period there has been lot of change, right. So, some Thomas who was your classmate when you were in fourth standard, it is not the same Thomas when he is aged around 20, 22 or so. There has been lot of changes, but still you are able to recognize him. Maybe that you have forgotten his name, that is okay, but still you can say that okay, I know this person, I have met him somewhere before. So, some sort of association you can do with some pattern that is stored in your memory. Okay. So, that is what is associative memory. So, given a pattern, even if the pattern is not perfect, it is an imperfect pattern. Still, if you have a pattern stored in the memory, and once an imperfect pattern, imperfect form of the same pattern or distorted form of the same pattern is presented, then you can recollect from the memory the perfect pattern which has been stored, which is very close to this imperfect pattern. Okay. So, that is what is the concept of associative memory. I can associate an imperfect pattern with a perfect pattern which is stored in my memory. Okay. So, here we assume that the pattern vectors or the feature vectors that we have are binary feature vectors, and whenever I have a binary feature vector, the normally by binary what we mean is the different feature components will be zeros and ones. Okay. So, in this particular case, every 1 will be represented by +1 and 0 will be represented by -1, but still it is binary because I have only 2 digits, one corresponding to +1 and the other one is -1. So, the feature vectors that we have are binary feature vectors, and suppose there are n number of components of the binary feature vectors. That means, I have n bit patterns. Okay. Now, the difference between the backpropagation network or multi-layer persiston and this Hopfield neural network is that in case of backpropagation network, your information flows only from the input layer to the output layer. Okay. A node in the k minus first layer will always feed to a node in the kth layer. A node in the kth layer will always feed to a node in the k plus first layer. Okay. But a node in the kth layer does not give information, does not feed a node in the k minus first layer. Okay. So, that backpropagation or backward information flow only we use for training the network, but not for computation. In case of Hopfield network, output of every node is connected to the input of every other node. Okay. So, it is something like this. So, if I have n number of nodes, okay, every node obviously has an input, that is a binary pattern, they have outputs, okay, and output of every node is connected to the input of every other node, and this connection is bidirectional. That means, information flows in both the directions. Okay. So, similarly from here, sorry, this goes to the input side, not from the output side. So, this connection will go to the input side. Okay, like this. Let me draw a fresh figure. Okay. So, like this, output of every node is connected to the input of every other node. Okay. And as before, the output of ith node is connected to the input of say jth node via a connection weight Wij. Okay. And this is the same connection weight which is used for connecting output of the jth node to the input of ith node. Okay. So, Wij and Wji for same and I and j will be same. Okay. And what you do is, by training as before, here what we are doing is we are actually storing a number of patterns, a number of binary patterns in this associative network or in this Hopfield network by adjusting the weights properly. Okay. So, it is the weights Wij which actually stores the patterns. Okay. And when you feed an input, because it is a feedback network, from every node I get input to every other node. So, it is a feedback network. Okay. And all the nodes can be fired or can be activated asynchronously, that is, in which order the nodes actually operate, that is not specified. They can work in any order. Okay. So, finally, when you feed an input, there will be a number of iterations which occur asynchronously among all the nodes, and finally, when the node stabilizes, when the network stabilizes, the output vector that we will get, it is one of the vectors which is already stored in the network by adjusting the connection weights, which is closest to the input vector that you have given. Okay. So, when you train the network, you train the network using the perfect feature vectors, and while retrieval, even if I give an input vector which is not perfect, the network will retrieve one of the patterns which is perfect and stored and closest to the imperfect input vector that we have presented. Okay. So, that is how this Hopfield neural network works, and while changing the output, while retrieving a particular pattern, okay, the output of a network will be set to +1 or it will be positive if sum of the weighted inputs is greater than 0, and it will be made negative if it is not greater than 0. So, for less than or equal to 0, the output of the node will be negative. For weighted input, sum of weighted inputs, if it is greater than 0, the output will be set positive. Okay. So, you find that during iteration, the output of a node can vary many times before it actually stabilizes, because every change in output of one node is reflected to the input of every other node. Okay. And as it is reflected to the input of every other node, so our change of output of one of the nodes may effectively change the output of some other nodes. Okay. And that change again may reflect the output of the previous node, because this change is again reflected to the input of the previous node. Okay. So, the network will go through a number of iterations iteratively, and during the iterations the output of the nodes may vary from plus to minus many times before the network actually stabilizes. Okay. And when it stabilizes, the output pattern that we get, that is the closest pattern which is stored in the network and closest to the input pattern that has been presented to this neural network. Okay. So, actually it is associating the input pattern to one of the stored patterns. So, that is why it is associative memory or associative network. Okay. So, now let us see that how we can store the patterns in the weight vectors or the connection weights from the ith node to the jth node. So, when we set the weight vector Wij, I have to consider the training patterns that has been given, that has been provided. So, suppose I have this pth training pattern xp, okay, and as I said that this xp or the training vectors, the sample vectors are n dimensional vectors. So, it will have n number of components, and let us say those n number of components are x1p, x2p up to xnp. As I have n number of components in the feature vector, each of these x1, x2, xn, they can assume either a value +1 or a value -1, because they are binary patterns, and our convention is that a bit 0 will be represented by -1. Okay. So, every component can have a value either +1 or -1, and this is the pth training vector, feature vector, and I have say m number of feature vectors. That means, this p, it can vary from 1 to m, as I have m number of feature vectors or m number of training vectors. Okay. Then using these training vectors, I have to compute the connection weights Wij. So, Wij is given by sum of xip into xjp, okay, where this p varies from 1 to m for all I not equal to j, okay, and it will be equal to 0 if I is equal to j. So, that is how you set wij. Okay. So, what does it mean? You find that whenever I is not equal to j, your wij will be computed by this. If I is equal to j, then wij is equal to 0. Okay. You find that when I have drawn this schematic of this Hopfield network, I have not fed back to the input of the same node. Okay. So, that means wij for I equal to j is equal to 0 means that a node does not feed back the signal to itself. Okay. The output of a node is connected to the input of every other node via this connection weights wij, but output of a node is not connected to the input of the same node. Okay. So, that is what it means. And from here you find that what is this term ij xip into xjp, you find that both these components are coming from the same feature vector p. Okay. And the feature vectors are binary feature vectors having values +1 or -1. Okay. So, this simply says that if xip and xjp both of them are same, both of them are positive or both of them are negative, then this term will be equal to +1. If one of them is positive, other one is negative, then this term will be -1. Okay. So, overall this summation sum xip into xjp. Okay. So, this simply tells you that the number of times the bits are same minus the number of times bits are different. Okay. So, that is how, and that is computed over all the training patterns, because it is from p equal to 1 to m. So, it is computed over all the training patterns, and that is stored as wij, the connection weight between the ith node and the jth node. Okay. So, let us take a very small example.
Sir, is there a rule that the connection should not be there for the upper nodes from the below nodes?
No, there is no such rule. I did not put it intentionally, because I said that it is the same connection which is used for bidirectional communication.
Actually, in that diagram, second one should be connected to first.
The output of the second node
Second one should be connected.
connected to the first node.
Yeah, it should be there. Output of the second one should be connected to the first one. From second one to second one, there should not be any connection. From first one to first one, there should not be any connection. Okay. But the connection weight will remain the same. wij is same as wji. Okay. Connection weight will remain the same. Okay. So, let us take a very small example to see how these weight vectors are really assigned. So, let us take that I have say 3 feature vectors. One is x1, and this feature vector is given by plus a 6-bit feature vector. Okay. The second one x2, which is given by okay. So, +1 -1 +1 -1 +1 -1, and the third feature vector x3, which is given by okay. So, all the 3 are 6-bit feature vectors. Okay. So, I have to compute the different connection weights. So, what will be the value of W12? Okay. So, here you find that I have to consider the first bit and the second bit. Okay. So, from the first feature vector, both of them are positive. Okay. So, when I compute this term xip into xjp, where I is equal to 1, j is equal to 2, that will be simply x11, that is plus, x 2 1 that is also plus. So, I get product to be positive. Coming to the second one bit is positive, the other bit is negative. So, it will be minus 1. Coming to the third one, both of them are positives. Okay? So, I will get plus 1. Now, when I sum over all these 3 patterns for p varying from 1 to 3, my result will be equal to 1. Okay. So, this W 1 2, this will be equal to plus 1. Okay. Similarly, and W 1 2 will be same as W 2 1, that you can easily verify. Okay. Similarly, when I compute W 1 3, okay, I have to consider the first bit and the third bit. Over here it is plus 1, over here it is also plus 1, over here it is also plus 1. Okay. So, W 1 3 I get, that is nothing but plus 3. Okay. What is W 1 4? Here it is plus 1, here it is minus 1, here also it is minus 1. So, effectively I get W 1 4 to be is equal to minus 1. Okay. Then W 1 5, here it is plus 1, here it is plus 1, here it is minus 1. Okay. So, it will be 1. Okay. Similarly, W 1 6, that will be plus 1, minus 1, minus 1, it will be minus 1. Is that okay? This computation. So, likewise, you will find that I have to compute W 2 3, I won't compute W 2 1 because W 2 1 is same as W 1 2. Okay. W 2 2 is equal to 0. So, I have to compute W 2 3. So, second and third. Okay. Here it is plus 1, here it is minus 1, here it is plus 1. So, 1 plus 1 minus 1, W 2 3 becomes plus 1. Okay. Similarly, W 2 4, take the second and the fourth bit, here it is plus 1, second and fourth bit, here also it is plus 1 because both the bits are negative. Okay. Second and fourth bit, it is minus 1. So, that gives me W 2 4 also equal to plus 1. Similarly, W 2 5, okay, second bit and fifth bit plus 1 here, second bit and fifth bit minus 1 here, second bit and fifth bit minus 1 here. So, I get overall minus 1. Okay. Similarly, W 2 6, here it is plus 1, here it is plus 1, here it is minus 1. So, W 2 6 is plus 1, right. Now, when I compute W 3 1 is same as W 1 3, I do not have to recompute. W 3 2 is same as W 2 3, I do not have to recompute. W 3 3 is equal to 0. So, I have to compute W 3 4. Okay. W 3 4, here it is plus 1, 3 4, here it is minus 1, 3 4, here it is minus 1. So, W 3 4 becomes minus 1. Okay. W 3 5, here it is plus 1, here also it is plus 1, here it is minus 1. So, W 3 5 becomes plus 1, and W 3 6, here it is plus 1, here it is minus 1, here also it is minus 1. So, W 3 6 becomes minus 1. Okay. Similarly, I have to go for W 4 5 because others I need not compute. So, W 4 and 5 plus 1 minus 1, here it is plus 1. Okay. So, W 4 5 becomes plus 1. W 4 6 plus 1 minus plus 1 and plus 1. So, this becomes plus 3. Okay. Then I have to compute W 5 6. because others I need not compute. Okay. W56 plus 1 minus 1 plus 1. So, it effectively becomes plus 1. Okay. So, these are all the weight vectors that I compute, which stores these 3 different patterns. Okay. So, once I have these weight vectors, then using these weight vectors, now if I feed in an unknown feature vector, after iteration, then when this network will converge, it will give me an output vector, which is close to the output vector will be one of these 3, and that will be closest to the input feature vector that you have presented, even if the input feature vector is not one of these 3. So, it will try to extract one of the stored patterns, which is closest to the input vector. Okay. Now, the question is, why should this network work? How does it work really? Okay. Suppose I feed in an input feature vector, binary feature vector, which is given as y, which is nothing but y1, y2 up to say yn. It should also have the same number of components. Okay. And given this, the output of ith node it will be either plus 1 or minus 1, and this output will depend upon, you have to compute wij times yi for j varying from 1 to n, and depending upon the sign of this. Okay. If it is greater than 0, then the output of the ith node will be plus 1. If it is less than 0, the output of the ith node will be minus 1. That will be repeated many times during the iteration, and finally, it will converge. Okay. So, this sign of the output of the ith node will actually change many times, not only once, and that will change asynchronously. I can't say that after change of the output of the first node, then only the output of the second node will change. There is no such guarantee, because everything works asynchronously, and all of them are working in parallel. Okay. So, you find that if you analyze this term, that is this summation of wij into yi, where j varies from 1 to n. Okay. If I analyze this, this will simply be sum of, what is this wij? Wij is sum of x I p into x j p, okay, where p varies from 1 to m. If I have m number of patterns, okay, this times y j, where j varies from 1 to n. Okay. So, this is what my w I j, right, and this term I can write as sum of x I p into sum of x j p y j, okay, where j varies from 1 to n and j not equal to I, okay, and here p varies from 1 to m. Okay. So, I can write this whole term in that manner. So, it is just rewriting this expression into this form. Okay. So, here you find that this value within this x,
I is not taken to,
pardon,
I is not taken, but
I will not be written because I want the ith output. So, my variable will be j. It is the ith output. Okay, so, I have to sum it over j.
like it's coming like a vector from all the neurons of the
It is the output of the ith neuron,
single value.
single value. Yeah. Okay. So, if I compute for all values of I will get the vector. Is that okay? So, here you find that depending upon the closeness of this vector x and y, this is the product of x j times y j, and you are taking the summation for I is equal to 1 to n. Okay. Where sorry, j is equal to 1 to n, where j is not equal to I, right. So, this value will be close to n, where n is the dimensionality, if the vector x j and y j, if the values x j and y j are matching most of the time, right, and this will be close to minus n if x j and y j they do not match most of the time. Okay. So, if they match most of the time, I get a positive output, and that means that this pth bit, whatever is the output, that should be the sign of the pth bit, that should be the sign of the ith bit. Okay. And if they do not match most of the time, then it should be the reverse. Okay. So, if you go on iterating on this a large number of times, when the network converges, the output of the network will be the one which is closest to the pattern which is stored into the network. Okay. So, that is the logic behind why this network should work as an associative network. Okay. So, I will stop this lecture today. Next day we will continue with some other topic. Thank you.